Divided difference due to Newton's divided difference formula, which is generally called Newton's general interpolation formula, can be derived in a similar way, writing f of x x0 as y minus y0 by x minus x0. So ultimately from the calculations we get the Newton's divided difference formula as y is equal to fx0 plus x minus x0 into f of x0 minus x0 x1 plus x minus x0 into x minus x1 of f of x0 x1 x2, like this, the last term being the remainder term. To use the divided difference formula due to Newton, we have to find out the divided difference table. It is a little bit different from the difference table as we have seen in the earlier. We should have two components, one x component, and on the right hand side we should write the y component. The divided difference are written in the way using both the components from the left hand column to the right hand column also. Newton's divided difference formula can therefore be written as y is equal to fx is equal to fx0 plus x minus x0 into divided difference of f of x0 x1 plus x minus x0 into x minus x1 into divided difference of f of x0 x1 x2 plus etc. plus x minus x0 into x minus x1 into x minus xn minus 1 into divided difference of f of x0 x1 up to xn plus the remainder term, which is rn plus 1, given by rn plus 1 is equal to x minus x0 x minus x1 up to x minus xn divided difference of f of x x0 x1 up to xn. This is the remainder term. So the Newton's divided difference polynomial is given by phi nx, which is fx0 plus f of plus x minus x0 into f of x0 x1 plus x minus x0 into x minus x1 f of x0 x1 x2 plus up to x minus x0 into x minus x1 into x minus xn minus 1 into f of x0 x1 up to xn. This is the Newton's divided difference polynomial. This is the expression which we shall use in our problems. As a part of the problem concern, let us consider the following problem. We are given with the following table for xi and yi. Given xi to be 3, 1, 6.0, 10.0, 15.0. Observe that xi's are not in order. This is allowed in the case of divided difference and also in Lagrange's. Obtain the divided difference table. I have used the abbreviation DD for divided difference. Obtain the divided difference table and find y at x is equal to 6.9. As we have shown in the earlier page, the table is formed. In the left hand side we have x series and on the right hand side we have y columns, and the divided difference can easily be obtained. For the divided difference 1, that is the 0.2386, has been obtained as 0.4771 minus 0.00, that is y0 minus y1 divided by 2.0, which is x0 minus x1. This comes out to be 0.2386. How the figure 0.1556 comes? It is 0 minus 0.7782, that is y1 minus y2 divided by minus 5, that is minus 5 means x1 minus x2. that is 1 minus 6, that is minus 5. So the result is 0.1556. Similarly, the divided difference 2 is obtained as 0.2386 minus 0.1556 divided by minus 3.0. What is 3.0? Minus 3.0 is x0 minus x2, which comes out to be minus 0.02767. Similarly, the other second order divided difference are being computed. Then, using the final expression for Newton's divided difference formula with x is equal to 6.9, we get y 6.9 is equal to, the computation is shown here, the final result comes out to be 0.8203. So this is the way by which we can determine the value of y at an arbitrary point x, but within the given region of our interest by using the Newton's divided difference formula. Let us now go to another type of problem. Suppose we are given with the following table: x for 0, 2, 4 and 8 not equispaced, corresponding y is 3, 8, 11 and 18. Obtain the Lagrangian and Newton's divided difference polynomial. There are 4 data points, so that there will be polynomials of degree at most 3. Let us first start with Lagrange's polynomial. We have the Lagrange's interpolation polynomial. We use this polynomial x minus 2, x minus 4 into x minus 8 divided by 0 minus 0.2, 0 minus 0.4, 0 minus 0.8 into y0 plus the other terms, which gives us x cube by 24 minus x square by 2 plus 10x by 3 plus 3. If we follow Newton's divided difference polynomial, the divided difference are 5 by 2, 3 by 2 and 1. The second order divided difference comes out to be minus 1 by 4 and 1 by 12, and the third order divided difference is 1.1 by 24. Then the divided difference polynomial comes out to be this one, and observe that this is the same polynomial we have obtained in using Lagrange's polynomial. So phi 1 and phi 2 are one and the same. If we use Lagrange's polynomial or Newton's divided difference polynomial, the polynomial will be the same if we use them on the same table. But here I would like to come to another type of interpolation, which is known as Hermite interpolation. So far, we have considered interpolation polynomial which take care of only the value of the function at the interpolating points. That is, yi is equal to fxi, where xi's are given, I is equal to 0, 1 to n. This may be equispaced or not. In case of equispaced, we shall use equispaced formula, but if they are not equispaced, then we shall use Lagrange's or Newton's divided difference formula. If we differentiate these formulas, then we will get a formula with respect to x, of course, differentiate with respect to x, then we shall get a formula involving dy dx. If we put x is equal to, say, any point, x is equal to, say, x, which is not coinciding with the given arguments, then we can determine the value of dy dx at that point. That is the slope of the function at the given point on the basis of the surrounding values of fx. This is the formula. Yes, very quite often we follow this formula. Just take the dy dx and obtain the separate formula for obtaining the slope of the curve at the designated point. But here lies a problem. So far as our experience goes, that this formula is not exact. In some cases, the exact value of the function is not coinciding with the computed or estimated value of the dy dx. This can be clear if we just look at the following graph. We have two curves here. One is some oscillatory character, which is the curve of y is equal to fx, and the other one is a curve is a straight line type curve, not exactly straight line, but a second order curve, a broken curve, which fits the values of fx. Yes, it fits the value of fx, which is called the phi x curve. Phi x curve fit the values of fx at the designated argument. But see that the tangent at the curve, which is denoted by f dash x, and the tangent to the polynomial curve, which is denoted by phi dash x, differ a lot. So what happens? That although we are able to interpolate the functional value by means of the interpolation formula, we are not able to obtain the slope of the curve by using the interpolating differentiation formula. So that is why we have to proceed to construct a function which takes care of the value of the function at the designated nodes as well as the value of its slope, that is the value of its derivatives at the designated nodes. In view of this, we proceed to construct a polynomial phi x which interpolates both fx and f dash x at the designated nodes. That is, the phi x should have the property that phi xi is equal to fxi so far as the values of the function is concerned, as well as phi dash xi is equal to f dash xi so far as the slope of the function is concerned at the designated point where I is equal to 0 to n. That is, there are n plus 1 points. So there are n plus 1 conditions regarding the values of the function and another n plus 1 condition regarding the slope of the function at the designated point. So that altogether we have n plus 1 plus n plus 1, 2n plus 1 conditions given to us. So there are 2n plus 1 conditions given to us. It is therefore we require to determine a unique interpolation polynomial phi x over the entire region AB of maximum degree 2n plus 1. Because there are 2n plus 2 conditions, we should have a unique interpolation polynomial phi x whose degree would not exceed 2n plus 1. Satisfying the 2n plus 2 conditions, phi xi is equal to fxi at I is equal to 0 to n, and phi dash xi is equal to f dash xi, I is equal to 0 to n, where xi's need not be equally spaced. So it is a problem to find a polynomial function phi x satisfying all these 2n plus 2 conditions. As I have already told you that the basic Lagrangian polynomial is of much use in our future discussion. Here we use the Lagrange's basic polynomial Lix and take which is a polynomial of degree n. If we square it up, we will get a polynomial of degree 2n. So if we take a Lix whole square, we get a polynomial of degree 2n, and multiply with it a linear polynomial, then we will get a function, a polynomial function which has degree 2n plus 1. In this way, the required polynomial function of degree 2n plus 1 can be written as h 2n plus 1 is equal to summation I is equal to 1 to n yi plus x minus xi within bracket yi dash minus yi into summation j is equal to 0 to n 2 by xi minus xj, j is equal to 0 to n but j is not equal to I, multiplied by Lix whole square. This is a 2n plus 1 degree polynomial which satisfies the condition phi xi is equal to fxi and phi dash xi is equal to f dash xi, and Lix, as I have already told you, that Lix is given by this formula. Here h2n plus 1 is a unique interpolation polynomial and is known as Hermite interpolation polynomial. Here yi is equal to fxi and yi dash is equal to f dash xi. This is the Hermite interpolation polynomial which satisfied, we take take care of both the functional value as well as the value of the function, derivative of the function, that is the slope of the curve at the designated point. h2n plus 1x can also be written in the following form. h2n plus 1 is equal to summation uix into yi, I is equal to 0 to n, plus summation I is equal to 0 to n vix into yi dash, where uix is given by 1 minus 2x minus xi into li dash square li dash xi multiplied by li x whole square, and vix is x minus xi into lix whole square. So let us clear it by considering one simple problem. X is given at the point minus 1, 0, 1. Y is given, the corresponding values of y are 1, 1 and 3, and the y dash, that is dy dx, at the same points are given to be minus 5, 1 and 7. Here there are 3 points, so that n plus 1 is 3, that is n is equal to 2, x0 is minus 1, y0 is 1, y0 dash is minus 5, x1 is 0, y1 is 1 and y1 dash is 1, x2 is 1, y2 is 3 and y2 dash is 7. We compute L0x. L0x is x minus x0 into x minus x1 divided by minus 1 minus 0 into minus 1 minus 1, which gives us L0x as half of x into x minus 1, so that L0 dash at x0 is minus 3 by 2. Similarly, other L1x and L2x and corresponding L1 dash x and L2 dash x. U0 comes out to be 1/4 of 3x to the power 5 minus 2x to the power 4 minus 5x cube plus 4x square. It is a polynomial of degree 5. V0x is similarly obtained as 1/4 of x to the power 5 minus x to the power 4 minus x cube plus x square. So here h5x, that is h2n plus 1x, comes out to be 2x to the power 4 minus x square plus x plus 1. You may notice that h2n plus 1 h5x is of degree x to the power 4. That is, it happens to be just by accident. The coefficient of x to the power 5 just cancel out it, but in some other cases we will get h5x as a polynomial of degree 5 also, but in this case accidentally the coefficient of x to the power 5 has cancelled out here. We may verify that h dash x2 h5 dash x2 gives out the value of 7, which coincide with the value of y2 dash. Here I should mention one point, that if yi are be known for one set of values of x's, but yi dash are known for another set of x's, then the problem of finding phi x, which will interpolate both the values of y and y dash, is really a problematic one, and there is no such formula.